Hello everyone, it's January the 2nd. Alright, first things first, I did the contest yesterday. I was better than last week, but still only able to solve 3 problems. So I solved 3 problems in 16 minutes. Oh well, 16-minute flat. And the last one took the rest of the time, was not able to handle. Actually, will show it later on. But a ranking, I think this is this the highest I've ever ranked? Actually, check. 1562. So yeah, that's what happens. You can only solve 3 problems. The fourth one's just. Oh no, I think the highest I got is 1536. Wait, what is this? 1536. What was my ranking? Is it 1536? 1562. Yeah, so it was not my best ranking. But, should I say? I mean, it's we're going up and down. So, yeah, that's the one. No, that's the bad ranking rank. I don't know. What does this point mean? Anyway, so that was that. I'm actually going to redo this. Not really redo. I already tried. This is the last question. The hard question. I already tried 4 different attempts, and they all fail. They all fail. So I think what I'm gonna do is I'm gonna try the hints and see if I can get an insight out of it. I mean, the last one was almost there. The last one was almost there. So take out the last one. I passed 91 out of 92 test cases, and I missed by 1. I mean, take a look at this. This is a giant, right? It's impossible for me to even try what went wrong. I mean, I have a little theory going on here, but apparently it's not working. So, bummer. Really bummer on that. Oh well. We'll figure it out. We'll figure it out. I mean, worst case scenario, right? We go through the hints, still can't do, and then we just go to discussion. But this is today's problem: pairs of songs with total duration, whatever this is, and it's done a while back. All right, let's take a look. You're given a list of songs where the ith song. Oh, by the way, before yesterday's contest was quite easy on the first 3 questions. Like the first one, easy, very easy, and then the second and third both can label as medium, but they're very easy. I mean, they're so easy that I started doubting myself, especially the third one. I started doubting myself. Like, is it what I think it is? Is it that easy? Like I wasn't even sure. But then I just go with it. I got screw it. I'm just gonna go with it, and it is. It's just like that easy. But the last one was a bomb. All right. Anyway, let's go back to this one. So ith song has a duration of time I. Return a number of pairs of songs for which their total duration in seconds is divisible by 60. Formula will want the number of indices ij such that I smaller than j, so I and j is not the same, thus divided by 60. The number of pairs of songs. So this looks like a 2-number question, right? Total duration, so 30 and 150, 20 and 100, 20 and 40, they're divisible by 60. And all 3 pairs divisible by 60, okay. All right. Let's take a crack at this. There's a little bit of pressure because I did it last time. Okay, so what are we looking at? Given the value 30, right? What we want to find is anything that. So what we can do is everybody divided by 60, right? Everybody divided by 60. Sorry. everybody divided by 60, and then we take the remainder. We take the remainder, and if there's a sum, then the sum of the remainder must be divisible by 60. Well, the sum of the remainder must be 60, right? And so we divide by 60, remainder will be 30, 20, while 60 be 30, right? So 2 times 60, 30, and 40, and 40. So that's the remainder. So for 30, we want to find 30. So 30 was 150. 20, we want to find 40. Yeah, and then I think that is about it. But how do you make sure that you will find all pairs? Let's see. Like this one will be 0, 0, 0, right? So 0, we'll find a 0. So count. Oh, we just find how many are there, and then we do combination, right? Yeah, so that will be 2, and that will be 3, and then this, so we have 0, we have these 2, and we say, okay, that will be 2, and then the next 0, okay, 1, that'll be 3. Hold on, how will we? So I know I my remainder 30, so I look into it, right? So the remainder 30, we have these things, and since I have remainder 30, then if it's a remainder 30, then the entire group, any pair can match, all right? If it's remainder 30, any group can match. So I just match everybody, yeah, because 30 is 30, that's good. If my remainder is 20, I need to look for 40, all right? So I look for 40, and then any 40, so all of them, right, we take. And then when we're looking at 40, how do we prevent the duplication? I mean, we prevent duplication by going all the way to 30, right? Because if we go to 40, we're going to try to find all the 20s. But all the 20s are already encountered. So we just go halfway. We'll go halfway through. So we'll have this, we can loop it, and we're going to stop by halfway. Because if we pass halfway, past 30, we must find something smaller than 30, and we must, yeah. Okay, so that's a strategy. All right, let's try it. So it's going to be 22. Wait, hold on. Wait, did I? Oh, wait. Today is January the 2nd. I don't know what I was doing. I thought today is January the 3rd. All right, so that's that. Hold on. Let me handle a few things. There we go. Okie dokie. Let's get this one done. So first of all, what we do is we're going to create a remainders, or equal to what? This for t in times. So what we're going to do is t mod 60. Oh, I need to append. My bad. So that's actually that's not it. From collections, import. What do we import? Default dict. Right, and then rems is going to be a default dict. List, then for t in time, say rems t mod 60, dot append t, right? Actually no. Actually no. Is int. We just need a plus, right? Plus equal 1. So once we grab this, then we're just going to say for R in sorted rams, right? And sorted R in sorted rams. If R is larger than 30, then we break. And I'm going to return res. Okay, I'm going to get a res as here. So if R is smaller than 30, then also should say if R is equal to 30, res plus equal to rems R C something 2 is this times as minus 1 divided by 2. So this times rems, right, R minus 1, the whole thing divided by 2, right? If it's equal to 30, and else if it's not, right? If it's not, then res plus equal to. So anything in my, so rems R times what? Rems 60 minus R, right? So everything in my and everything in this, that can be, yeah, so that. Okay, so let's run this one. So we have first is this times 3. Second is 60, 60, 60, I remember. That should be 3 as well. Okay. So when the passing time, this will be num pairs, blah, 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 time. Run it. Uh-oh. That is weird. O equals 30 or R equals to 0. Because these are the only two that can handle, yeah. Okay, let's try this. Go. All right, so we did not improve at all. Right, that's the same solution. I bet you it's the same solution as I had back then. So this is pretty bad. 524. All right, we'll go 524 milliseconds and only 5% ranking. Wow. So what's the runtime on this? O and log n, because we have a sorting, right? Find the remainders for all time and match the two remainders that add up to 60. I'm pretty sure that was the same solution as I had back then. It's off the chart. I have a bucket. Hey, whatever this is, I don't know. It's recording this and then multiply 6. Yeah, I don't understand. Just by reading through it. 1 to 17. What are these values? 17. Oh, time I has a limit of 500. So it's a different solution. Oh, okay. But it's bad. All right. Show me. What is this one? Wait, I mean, think about it. Can we do better? I mean, maybe we don't sort? I mean, yeah, we don't have to sort. We just, once we're done, we just remove them. How about that? Let's try it. So basically when we say while rems, yeah, we cannot say while rems. Yeah, we can say while rems, right? While rems, what are you gonna get out? No. We can go from 1 to 60. And this one we only need to run for r in range to 60, right? And then we say if r is in rems, then if r in rems, and then if r is this, yeah, and then we do this, else we do this. Once we're done, we say, I shouldn't say if r in rem, we just say if rems are, right? If rems are, once we're done, rems r equals rems 60 minus r equals 0. Right? So we go 1 to 60. I mean, actually, we don't have to go 1 to 60. We only need to go 1 to 31, because we only need to go to 30. This might be faster. Right? If it's 0 or 30, we need to do this. If else, we just match the other, and then we set those to 0. And actually, we don't even have to set it to 0, because we go 0 to, yeah, we don't even have to set it to 0. Yeah, we don't even need to do any of this. We just go like this. Right? We only run 30 times. All right, let's see if we can get it faster. Now, this is just on, because we do have to put all the time in it. So this is on. Try it. Yep, that was one faster. This is on, which only run at 240 milliseconds. 46. All right, let's see. We have a 200. Is that a 200 millisecond? Yeah. Oh my goodness. Yep, it's the same thing. C0, C30, and then we go 1 to 30. That's true, 0 and 30 can be considered separately. But some this time is nice. So yes, it is the same. Counter. Why don't you use counter? Stupid. Yeah, this can be counter. Right? Counter. t in time. All right, we do a counter, and then yeah, use a counter. But we have the same idea. All right, that shall be it. Cool. All right, back to this maximum employee. Maximum employee. So it's my latest attempt, which is also wrong. It's the latest attempt. All right, let's see the hint. From the given array favor, create a graph with every index I. There's a directed edge from I to I. The graph will be a combination of cycles and chains. Yes. What are the ways in which we can choose employee to sit at the table? Yeah, if it's a cycle, then all of them are doomed. If it's a chain, then all the chains can concatenate. That was my intuition from last night. Yeah, they can always concatenate. The first way by which we can choose employees is by selecting a cycle of the graph that do not lie in the cycle can never. Yes, I did that. The second way is by combining acyclic chains. The most two chains can be combined by a cycle of length 2, where each chain ends on one of the employees in this. This I do not understand. We can combine acyclic chains. We can combine any number of them, acyclic chains. Because the requirement is they sit next to the ones that they enjoy, that they're their favorite, right? So I can put two chains. I can concatenate any two chains because they all always sit next to the person they enjoy. At most, two chains can be combined by a cycle of length 2. Now this I do not agree with, and I call it the sticky ends, right? So this one, can we sit next to another one? Like this one goes here. Because this does sit next to, this does sit next to. Because the example given us, right? 3 sit next to 0. It can also sit next to 4. It's fine, right? So this one is 3 to 0, 0 to 1, 1 to 4, and a 4 to 1. So that is a chain, right? That is chain ending at 4. And this chain can be concatenated with any chain. So I don't know why this one is not right. I say all paths can be concatenated, but something is not right. I mean, it could be. I don't know. Let's try this. Oh, it might be a good idea to do it here. We'll see. That's fine. We can handle it. Expect is 25 I think it's just, oh. Okay, I see what this one's doing. This one has 0, 0 to 1, 1 to 0, 0, 1, 2, 2 to 1, 3 to 2, 4 to 3, all the way to what? This is 0, 1, 2, 3, all the way to 2500, right? It's all the way to 2500. So, but actually it's 25,000, and a 1 will go to 25,000. So that is the chain. So with this chain, we can sit 2501 to 2500 all the way to 2, we'll go to 1, 1 to 6 next to 0, right? And 0 next to 1. Unless there's something inside that I don't know. We cannot check, because based on this, I say is how many total people in this one? That is 25,002 in total. So 0, 1, 1, 0, right? And everybody else. Shoot. Let's see if this is a is this a full link? How do we check? Well, I'm not sure if it's a good idea. Might not be a good idea. Yep, it's not a good idea. Yeah, too much data. Yeah, I don't know. I mean, this is the only one that failed, so it will be good if I can figure out. Hold on, let me not do this. Can we cancel this? Jeez, can't even cancel it. Oh, now we good. Yeah, that's way too much better. No, I don't want to run in the REPL. Yeah, it's way too slow. I mean, it's simple. All we want to do is just to check if there's anything, right, weird going on. So we need to say A equals this, right? And then we say for B in A, for I B in numerate A. Right? If I is not equal to B, print I and B. It's not responding. I must close it. Unfortunate. All right, let's run this. Oh, it is not. I was. Oh, and more values. Okay, so wow. So we have 0 to 1, 1 to 0, and all the way to 2, 4, 998. Actually, it's 24999 pointing to 1 again. And then, because that's also 2 all the way to 2. Wait, hold on. No, that's not 24999 because I think that's 25000 pointing to this. And then we have 24999. So this one pointing here, and then 25001 pointing to 2. Right? And this one goes all the way down to right, pointing to the last one. That is interesting. Well, in this case, longest shall be why don't we print it out? Why don't we print what do we have? Anchors. Okay. This is anchors. 1. And then we have 0, 2, 0, 1, 1, 2, 3, 4. Yeah, that's one group. Right, so one group all the way to 24998. So 24998 going to 1. Right, so 24, we have 24998, and then going to 1, we have 24998 number of people. And then for 1, and 24998, and then at 1, right, have another group is 1, 0, and that one, 1, 0, has 2. So with this one plus 2 minus 1, which give us 24999. Right? That's the total value in this one. And then we have 2500 pointing to 2500, right, has length 3. I mean, if we pick, so what we do is we pick the largest, right? So okay, so this one, blah blah blah, blah blah blah. They grow, and at the end we have 49996. We have 49996 pointing to 1 with 24999. And we have, what are these? Are these branching out? Two, 4999 pointing to 1. 24999. No, 24999 is pointing to 2. Right? 24999 is pointing to 2. Wait, no. 24999 is pointing to 1. That is a different. And 49997 is pointing to 24999. Wait, don't we have 24999 already? Oh no, that's 24998. We don't have 24999. And 49997 is pointing to 24999. Right? 49997 pointing to 249. So what we have is, oh, screw me, man. And 49998. Man, we need to print both. Come on. So we need to print this. Of course, we don't need this. All right. And what we need is print this. Let's print adjacency as well. Okay, so now this is the adjacency. All right. So we kind of can check. Let's check 24998. So 24998 pointing to 24999, right? So it's 24998. So we go here, we check for 24998. 24998 has 24998 towards 1. So 24998 pointing to 24997. Right? That's all the one. Yeah, so that's correct. And 24999 pointing to 1. Okay. So this is 24998 pointing. So that's one range. Okay. And then we have 24999 pointing to 1, right? And 25000 pointing to 2, and 25001 pointing to 3, 1 out. And all the way, let's also find, so Control F, 24998. Who points to 24998? We have this. 49996 is pointing to 24998, right? And because they only pointing to one of them, so they only increase it by 1. So 24996 shall have a larger. So if we look at, oh no, shoot. Wait, which one's which? Screw me. This, I'm putting here. This is the adjacency list. This is the count. So we need to find 49996. So 4996 is 4996. This gives me 24999. Right? 24999. Yes, 24999. And plus 1, that gave me 25000. So this whole stretch, right, gave me that, which is correct. But the maximum I have is 24999, right? And if you look at the first, we have a 2, and this one we have a 3. Freaking 49997. Which one do you pointing at? 49997 pointing to 24999. So 49997 pointing to 2499, and 498 pointing to 25000. Where is 4998? 49998. 498 is 4. Huh? Wait, hold on. Is 4. Oh, is because where do 25000 pointing at? 2500 pointing to 2. Ah, yes, so that's here. 49998. Okay? So now everything is clear. I know how the entire thing works. So this one, so we have here is 1, 2, 3, 4. That's 4, right? And we have another one is 24999. Okay? And they all anchor at 1, right? So we have 3 paths anchor at 1. And my argument is what we shall do is 24999 plus this is 25001. Why is it not? Why is it not? Yeah, exactly. Why is it not? 24999 pointing to 1, right? And 2 pointing to 1. Oh, shoot. Because 1, oh my goodness, that's correct. They point into 1, but 1 is not the anchor point. I mean, 1 is the anchor point. But the anchor point requires that it has a, right? But 24999, when it points to 1, I mean, when 2 points to 1, 0. 0 is the anchor point. For crying out loud, 0 is the anchor point. I did the anchor point wrong. 1 is not the anchor point. I see. 1 is not the anchor point. How did we get to 1 is the anchor point? Well, because we start with 0 to 1 and a 1 to 0, right? Depending on which one we go, and that will become the anchor point. And then everybody will. But if something pointing to 1, how do we identify the anchor point? So we go 2 to 1, right? And so 0 to 1, 1 to 0. Now what we grab here is a pair, right? And then we have other things pointing to 1. And we think 1 is the anchor point, but 1 is not the anchor point. The anchor point shall only have one of them pointing to it. Wait, actually no. We can have other pointing to the anchor point, but the anchor point has to be at the end, right? Has to be at the end, which means if we go to the end, right, and I'll have this. We have a down and back, right? We have a down and back. That's what happens here, because we start with 1 to 0, okay? So 1 to 0, and then we go 0 to 1. So in this case, right, 0 to 1, we go backwards. So we go backwards, 1 to 0. No, that's 0 to 1, my bad. 0 to 1, and right, 0 to 1, and 1 to 0. Then I consider 1 is the anchor point. But in this scenario, 0 can be the anchor point as well. What we know is that is a pair, right? That is a pair. Let me think. And then we have something pointed to 1, right? Yes, it can be. 1 can be thought of as the anchor point. Now, what screwed things up, right, is, yeah, we can treat 1 as the anchor point. It's fine. But 1 is the anchor point. We need to have, like, 1 has to be next to the one it likes, right? So what I mean is, yeah, 1 is the anchor point, and we have 3 things pointing to it. But when we do this, 1 is no longer the anchor point. Why is 1 no longer the anchor point? Well, 1 is the anchor point if 0 is involved, right? Therefore, if I am the anchor point, then one end must be ending. One end must be a 2. Let me think. Right? A pair, like if I consider 1 as the anchor point, and we have a pair, right? And then we have a pair. Then that means this goes out. This has to go somewhere. It goes back. Yeah, if it's a pair. Yeah, so we always need to grab a pair for this anchor point. So it cannot be, yeah, if it's not a pair. The anchor point is the end, right? And then they have so many coming in. Right? They have so many coming in. It depends, right? 1 is the anchor point, and if they come in with how do I solve this? Now, what happens is if I have multiple pointing to 1, right? If I have multiple pointing to 1, it should be like this. If I have multiple point to 1, and 1 has pointed to an anchor point, we think this is the anchor point, right? And there could be 2 situations. One situation is this anchor point has multiple 2's sticking out, and we have another one. But we don't know if that one has a 2. That could be like 1 to 2 or 1 to. But no. Because 1, if that's an anchor point, it can only lead out to 1, right? It can only lead out to 1. So for the anchor point, the doubles can either be hidden in one of the long chain, right? If the doubles is hidden in one of the long chain, and then, but we don't know which long chain it hides. We don't know which long chain it hides. Oh mia. We need to know the chain that the double hides. And we can pick as anchor point. That's fine, right? So it goes. That's the anchor point, and that should be the main chain. This chain must be involved, right? If we want to do concatenation, this chain must be involved, and each chain must have an anchor point. And we have proved that as long as each chain has an anchor point, we're good. We're good to go, because everybody will be sitting next to their favorite. So that's fine. So every chain can be concatenated with each other. That's fine. So what is not fine is for each anchor point, we need to make sure that when we combine multiple within the anchor point, one of them must contain the double, the back and forth, right? One must contain that. So we need to pick that one out and then pick the largest among the remaining. How do we do that? How do we do that? Well, we can do that by set, because we know a back and forth, right? So we know a back and forth. So when we do back and forth, we can say, how do we know that they belong to this chain? Oh my god. Oh, remember, this is a dictionary, right? So if I take a look, this is a dictionary. And we just need to record. We don't need to record. We know 1 is anchor point, right? And 1 must be next to 0. So we just look for which group contains 0. That will be the main group. And then we find the maximum of that group, deleted it, and find the maximum amount. Okay, that seems to be working. So we don't have to change any of the code. What we need to do is for groups in anchor.value. No, we need anchor as well. So for anchor groups.items, right? So for each anchor, so if len groups equals 1, which means for this anchor we only have 1 chain, so definitely this. So we need to find the chain that contains the neighbor of the anchor. This chain must be included. This chain must be included. This chain must be included when we concatenate multiple groups. When we concatenate, it must be one of the two groups that can concatenate. So what we do is the neighbor will equal to favorite anchor, right? So we find the neighbor, and what we need to do is go through all of them, find which group contains, and that will be the one. So we're gonna say for G in groups, right? Can do this. Longest is 0. Actually, longest is -1, so we can just add, right? So then for G in groups, we say if G, if this is not, if this is in this group, right? If this is in this group, then longest plus equal to max G dot values, right? If it's in this group, then we must include it. But then we don't know how many we have included, right? So I'm going to say num included will be 0, right? Then num included plus equal 1. So I'm going to say if num included equals 2, then break out. Otherwise, we do this. If that's 2, then we break out. If not, then we need to keep going, right? Else, if this is so, we need to also sort, right? Oh my god, damn. You know what? No, I don't like this idea. I think I would just, yeah, you know what? Just for G in groups, if this is in G, right? Because it will only be in one group. Can it be in multiple groups? No, it cannot. Because if it will, yeah, it's just one chain. Right, it will be another one directly going to it. So no. So if it's in G, then for G in groups, so longest plus equal to this. How do we find let's do this again. So longest will be this, right? So for G in groups, if longest, and we need to do the, I will call it temp. Screw this. I'll call it temp. And we just go temp plus this, right? So we'll go through every groups. If the favorite of anchor is in the group, right, then temp plus, we must include this. Right? Else, then we just say longest dot append. Oh, we don't have to. We just need to find the longest among them. So what do we do? So we're going to say max len, right? So max len equals 0. And then we just say max len equals max len max G dot values, right? And then temp plus equal to max len at the end. And then some, oh, I don't have to. We got the max len. Oh, we don't even need a temp. So, oh, let's say max len, and then max none what do we call it? Non anchor length. Oh, it is anchor length, and then we call it max. Oh my god, I can't name this. Max non back and forth length, right? And when the other one would be the back and forth length. Right, both are 0. So we just got this will be back and forth length, and this will be max num BF length, back and forth length. So this will be BF length. This is max non BF length. All right, max non BF length. So we're just gonna do BF length plus max non BF length minus 1. So max non, no, so BF length is the length of the chain that contains, right, that contains the neighbor, contains the favorite neighbor of the anchor. This chain must be one of the two chains to concatenate, right? And then max non BF length is the max length of the chain that does not contain the anchor's favorite neighbor. Okay, so we do this, blah blah blah, and then we do this, and then we run it. Then we pass. Okay, I don't want to print anymore. Okay, took a long time. We pass. All right, let's try to run the others. They all pass. Oh, this one is promising. This one is very promising. Okay, so let's go to, all right, 5th try. Let's go. Nice. 5 tries. Oof. This is indeed difficult. Alright, this is indeed difficult. Okay, so now we need to try to summarize what we have found. So the intuition is, so how should we say it? So if we treat favorite as a graph, there are only 2 possibilities. One, the graph leads to a cycle. Once this happens, only the nodes in the cycle can be seeded. None other can join the cycle. Therefore, as we traverse through the graph, if a cycle is found, it's the length of the cycle can be directly compared and stored in the final result. 2, the graph leads to a chain that ends like this. Right? That ends like this. All such chains can be concatenated. All such chains can be concatenated without issue. Can be concatenated. Therefore, the job is to find all these unique chains. Now, they are differentiated by the anchor point. Given A, this, B, right? Which means A's favorite is B and B's favorite is A. We can pick any one of them as the anchor point. The complication is when multiple chain ends in the anchor point. That is also what got us wrong. For instance, we can have 0, 1, 2, 3, right? And let's say 1. Can we do this? Say 4, 5, right? We can have this. And let's assume 1 is the anchor point. Right. So 1 is the anchor point. So we have chain 0, 1, 3, 2, 1, and 5, 4, 1. All right. Within these three, only 0, 1 and 3, 2, 1 can be actually let's add one more. Yeah, only 0, 1 and this, or 0, 1 and 5, 4, 1 can be combined to form a longer chain. 3, 2, 1 and 5, 4, 1 cannot be combined because a chain of 5, 4, 1, 2, 3 does not have 1's favorite. Therefore, for each anchor point, right? For each anchor point, if there are more chains ending up, right? Ending with the anchor point, the only way to incorporate the multiple chains is that one of such chain must contain the favorite, contain the anchor's favorite. Now to maximize this combination, the other chain must be the longest among the rest. So so this analysis produces one chain, right? One chain for each anchor, one longest chain, one longest valid chain for each anchor point, and all of these chains can be concatenated can be legally. Thus, the result from the chain is the sum of all longest valid chain from all anchor points. Now, to represent for implementation, my choice is a dictionary with anchor as the key. Its value is a list of dictionaries, with each inner dictionary being a chain that ends in the anchor. The key of the inner dictionary is the node, and the value of the inner dictionary is the number of nodes from the key node to the anchor. This design allows any newly encountered node to know immediately how many nodes it is away from the anchor by checking its favorite neighbor. Yeah, current can lead to anchor with a group. And I'll just do. All right, so I don't know the runtime. This is actually I know, because helper runs on. This one runs on, because we only do this when we have it. So every node will be run at most twice. I think this is on, and this one. Yeah, I don't know. I don't want to know. Let's just record this and check the answer. 75. All right, so I'm going to read DFS. Oh my god, it is. Oh my god. You should comment. They have very good taste in game. Yeah, and this is the resurrection. This is the new version. It's not the one I played. You can see the graphics, and also they changed the arrangement of the menu bar. Wow. Good taste in game. Best game. Well, I cannot say which game is the best because I have very limited game experience. All right. Topological sort. Disjoint union. I was thinking about using union find. All right, let's read. I think this is on. I don't know. Maybe it's on. This is very complicated. Oh my god. Oh wow, it is long. All right, two nodes are interdependent. We can DFS from these two nodes backward to find the longest two arms. Say their lengths are A and B. We can form a free component of length A plus 2 plus 2. By free component, I mean if there are multiple free components, we can put them together in the answer, so we should run all the free components together. Yeah, cyclic is just cyclic. So this, in my case, right, I will consider, doesn't matter, whichever comment becomes the anchor point. One is the anchor point, right? So we have, this will be one group, right? Because this one points to one, so this is one group. This is the second group, and these two groups can combine, which is, in my case, is 1, 2, 3. But it would be 4 plus 4 minus 1. But of course, in here it's different because I think they consider this as the anchor, which is valid, right? Which is valid if we consider this as the anchor. And then we just find everything pointing to, so it'd be 2 plus 3 plus 2. Okay, that's valid. All three components in the same cycle. Yes, that's true. All of these chains can be concatenated. So that's the same. This is the same idea as I have, right? Exact same. They might have different implementation. I don't want to go into their implementation. I like my implementation. It's not the best, but I think I understand. Like, well, they have the traverse as well, right? Because as you traverse, I feel like this is the all right, so this is the same idea. I'm just gonna pictures. So let's go topological sort. Question error. Why? All right, topological sort. Find the loop of size larger than. Oof. Man, Java looks like C++, right? The goal is to find loops of size larger than 2 and loops of size equal to 2, with the longest path leading to either and. Yes, topological sort seems to be a good fit. Wait, how do you do topological sort? Um, in degrees and out degrees. Okay, so topological sort. In degrees. I to favorite I. So in degrees j. J's in degree because j is favorite I. So in degrees for j increases. So we have in degrees for each node. We have in degrees. So we find in degree as 0. Yes, in degree is a 0. That is the most outside. Yes, most outside. So okay, Q is over Q. Then every node, and then we say if the degree is 0, visited I is true. Q dot offer I. So we put I into the Q. Okay. Now DPI is the longest path leading to I exclusively. DPI is the longest path leading to I. Longest path, okay. So while Q is empty, is not empty, we pull it. So this one is, well, we can do this in Java. Yes, you can, because this int is defined inside the for loop. It has nothing to do with outside. And this is defined inside the while loop because it's inside here. So, okay, so yeah. So we define I as q dot pull, so we pull out, so that's the in degree of 0, right? And we find its neighbor, right? We find its neighbor, and dpj will be max dpj, whatever it has, and then dpj plus 1, dpi plus 1, because I leading to j, right? We want to find how many, the maximum length of node leading to j. And what we currently find is I can go to j. I can go to j, right? So if I can go to j, and we want to find the maximum length that can go to j. So basically is max this and then dp I plus 1. Yeah, that's true. And for j, if it's in degree, it's 0. So we minus j minus 1, right? If in degree is 0, we will offer j. So j becomes the next one. But if it's not, in degree is not 0, then that is not the outer layer yet. So when we do this, we'll grab. What this one does, we'll get the longest path ending in every single node, right? Longest path ending in every single node. Now, not visited nodes are all loops. So we have some nodes are visited, some nodes are not visited. Not visited nodes because they have an in degree. Yes, yes, because they are in a loop, right? They're in a loop. They will never be visited, right? They will never be visited because they're always the in degrees of 1, right? So loops of length larger than 2, and this will be loops of length equal to 2, and the path leading to both nodes. Yes, yes. So we do this. If this is false, then this must be in the loop, right? Yes. So we want to find the length. So we need to go through, right? We're going to go through the entire loop. So j, yeah, so we just keep going until we visit everything. Okay, so yeah, so we find I, so that is like the starting point of the loop. Then we just keep going, then we just visit it, go to the next one, until we, so now we get the length. If length is 2, right, then because we start from I and the favor is this, so we just do this. Oh, wow. 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 Hmm. It's good. It's very good. It's very, very good. Wow. Wow. Can't even spell. This is how you say beautiful, right? Yeah. So clear. So clear. Topological sort. Ooh. And we have one more. Disjoint union. Yeah, so they just join them. That's fine. Right? That's fine. You can join them. So your topological sort first, and then you're trying to find. Now I like the DP solution. I like the DP solution. All right. So what do we do now? We credit this one, and then so we credit this, and then try to write our version. Honestly, this is not too bad, right? This is not too bad. But yeah, so we have to handle like which one is the anchor point, but this one does not. Because topological sort, it find, okay, so I think the key insight is how do we identify? How do we identify the cycles in a graph? We find all the cycles by using topological sort. And this one is, we know that if it's a cycle larger than 2, that will be the solution. That will be one possible solution. If the cycle is 2, which is a juju, we notice that with a juju, right? We have a juju, then that will be the anchor. The anchor point is not a single one. The anchor point is a cycle of length 2. And then we just, from length 2, we will extend, right? Oh my god, so good. So good. All right, let's do this. Yeah, so topological sort. So good. Reference. So I'm gonna credit this dude. All right, so my understanding. So the problem, we have found the key to the problem in solution 1, but it is not clearly, it is not clearly identified. The clear explanation is that we need to find that there are two possible, right, solutions. One is a cycle of size larger than 2. This cycle can only exist by itself, so its size is a candidate solution. 2 is chains that anchor at a cycle of size equal to 2, which is this, right, in solution 1. Now the drawback of solution 1 is that we have to pick one of A or B, one of A and B, as a single anchor point. But in reality, an easier way to see this is to consider A, B, or a cycle of size 2 as the anchor. Now, from this anchor, we can have chains extending out from A or from B, and the total, right, and the total length, the total size of this chain is the length of the chain ends, length of the longest chain ends at A plus the longest chain that ends at B plus 2. Right? Topological sort is a very neat tool to handle this problem because after topological sort, we can easily identify all the loops, all the cycles, right? All the cycles. Then also along the way, we can compute the longest, right? The longest chain size ending at each node. Thus, all we need to do is to find the length of each cycle and treat them accordingly, according to their size. Alright, so this is how we should do. In degrees, as always, in degrees, so we have n equals len, favorite. So in degrees, so everybody's in degree. That would be 0 times n. Visited, 0 times n. Alright, let's try not to see this. Visited is 0 times n. Then we're gonna do topological. So now we can do this. Obtain, right? Obtain the in degrees
of all nodes. Right. So let's say for I, right, fav in enumerate favorite. So we have I to favorite, right? So in degrees of favorite plus equal 1, all right? Enjoy. So in degrees of this plus equal 1. And now we grab all the in degrees, and then we need to go topological sort, right? We're going to do topological sort, and to identify cycles and keep track of the max chain size ending at each node. So we have max size, it's going to be 0 times n, and I visited is equals this. Well, actually, let's do false, false, right? For fun. And then q will equal to, I'm going to say for I in range n, right? If not in degrees I, then q equals this, right? And then q dot append I, and visited I equals true, right? Then while q, right? So while q temp equals this, right? I'm going to say for node in q, right? For each node in q, we know its favorite is equal to favorite node, right? Therefore, we're going to say in degrees fav minus equal 1, because we visited this, so in degrees of minus equal to 1, and dp, not dp, max size, favorite equals max size favorite, and then max size node plus 1, right? Once it's done, we say if not in degrees favorite, right? If not in degrees favorite, then do you want to do this one here or do you want to do this one there? Actually, I want to do here for this. Then we can say we visit it, right? And then if not in degrees, so not in degrees, then temp, right, dot append favorite is the next one to check. So when we're done, q equals temp. All right. So once we're done, so after topological sort, so the nodes that have not been visited must form cycles, right? So we need to find the size of all cycles and treat them accordingly. So for I in range n, if not visited, right? If not visited I, then we need to count the cycle length. How do we count? We say while not visited I, right? Well, not, so we're going to say node equals I and size equals 0. So not while this size plus equal 1, node equals to favorite node, right? And then go back up. Oh, and then size equal to 1, and then visited node equals true. Then node to the next one, right? And then so we'll come out, so we can compare the size. And we say if size is larger than 2, then I'll have a res 0, right? Then we say res equals max, res and size. Else, so this is size equal to 2. If size equal to 2, then we have I and then this. Then so res equal to 0, right? And then we're gonna say chain comb length. Chain's length equal to 0, right? Then I'm going to say chain's length plus equal to 2 plus max size I plus max size favorite I, right? And then once we're done, we return max result and a chain's length. Okay, so try solution 2, pass. Good. Try it. Good. It's a matter of runtime, but this is much easier than this one. Right? This one, the representation is a little bit hard to wrap my head around, but this one is very simple, straightforward. Topological sort, right? And then, yeah, the topological sort. Once we're done, we just look for the cycles, and then boom, done. Beautiful, beautiful. Wow, that's it. That's it for today. I mean, I still think it's going to be a long way before we're able to solve a hard one in a contest. But we're trying. We're trying. All right. I'll see you guys tomorrow. Adios.